On December 27, 2004, at 21:30 UTC, something hit Earth. It came from 50,000 light-years away, from a dead star in the constellation Sagittarius, and it traveled at the speed of light for 50,000 years before reaching this planet. When it arrived, it ionized Earth's upper atmosphere in a matter of seconds, to a depth that normally only solar radiation achieves during the day. It disrupted radio communications across the night side of the planet. It saturated the detectors on satellites that were not pointing anywhere near the source. It lasted 0.2 seconds at peak intensity. Most people on Earth on that day had no idea it happened. The event was not visible to the naked eye, not felt, not heard. It registered on instruments. Scientists who analyzed the data afterward called it the most energetic event ever recorded from beyond the solar system to directly affect Earth. In the 0.2 seconds of peak emission, the object responsible released more energy than the Sun has produced in the last 250,000 years. The object was a magnetar. It is still out there. A magnetar is a type of neutron star. Neutron stars form when a massive star, typically between 10 and 25 times the mass of the Sun, reaches the end of its fuel supply and its core collapses in less than a second. The collapse compresses protons and electrons together into neutrons, producing an object roughly 20 kilometers in diameter with more mass than the Sun. The density is extreme. A teaspoon of neutron star material weighs approximately 10 million metric tons. Most neutron stars spin rapidly and produce strong magnetic fields. That is what makes pulsars, whose rotating magnetic fields sweep radio beams across space like a lighthouse. Magnetars are a subset of neutron stars with magnetic fields far beyond what ordinary pulsars produce. The magnetic field of a typical neutron star measures around 10 to the 12th power Gauss. A magnetar's field reaches 10 to the 15th power Gauss, 1,000 times stronger. Earth's magnetic field, for comparison, is roughly half a Gauss. A field this strong does things that have no analog in any other physical environment. It distorts the shapes of atoms, elongating electron orbitals in the direction of the field lines. It warps the fabric of space in its immediate vicinity. It stores an enormous amount of energy in the star's interior and crust. And it makes the crust of the neutron star, a crystalline lattice of neutron-rich nuclei, mechanically stressed in a way that eventually breaks. When the crust breaks, a starquake, the magnetic field lines reconnect and rearrange in milliseconds. That rearrangement releases the stored energy all at once. The result is a giant flare, a burst of gamma radiation and X-rays so intense that it qualifies as one of the most energetic events the universe produces. SGR 1806-20, the magnetar that fired at Earth on December 27, 2004, had been known to astronomers since 1979. It had produced smaller flares before. Nothing in the observational record prepared anyone for what it did on that December night. The flare from SGR 1806-20 on December 27, 2004 is the brightest extragalactic event ever recorded to affect Earth. The numbers involved are difficult to hold in the mind simultaneously, so it is worth going through them carefully. Peak luminosity, approximately 2 times 10 to the 47th power ergs per second. For context, the Sun's total luminosity is about 3.8 times 10 to the 33rd power ergs per second. The magnetar, at peak, was emitting roughly 50 trillion times more energy per second than the Sun. It briefly outshone every other gamma-ray source in the sky. All other known magnetars, all pulsars, all active galactic nuclei in the observable universe, combined. Duration of the main burst, approximately 200 milliseconds. Everything above happened in less than a fifth of a second. After the main burst came a pulsating tail lasting about 380 seconds, pulsing at a rate of 7.56 times per second, the rotation rate of the magnetar itself. The tail was generated by hot plasma trapped in the magnetar's magnetic field, radiating as the field reconfigured after the flare. The pulsation rate confirmed the signal's origin. A rotating neutron star, 20 kilometers across, 50,000 light-years from Earth. What this did to Earth's atmosphere was measured in detail by multiple instruments. The flare ionized the D layer of the ionosphere, the lowest layer, at altitudes of 60 to 90 kilometers, to a level normally only seen during solar activity at the peak of the sunspot cycle, or during a major solar flare hitting Earth directly. This happened on the night side of the planet, where the D layer is normally at its most relaxed state. The sudden ionization disrupted very low-frequency radio propagation, affecting navigation signals used by submarines and certain aviation systems. The effect lasted for several minutes after the main burst, as the ionosphere slowly recombined. No physical damage to infrastructure was recorded. The disruption was real but brief, and its scale, while unprecedented for an extragalactic source, was far below what would cause harm at ground level. The atmosphere absorbed the radiation before it could reach the surface. What scientists measured was the atmosphere's response to a hit, not a hit that got through. SGR 1806-20 is approximately 50,000 light-years from Earth. The flare that ionized the ionosphere came from that distance, crossed that distance at the speed of light over 50,000 years, and still had enough energy to measurably alter Earth's upper atmosphere on arrival. This raises an obvious question. What would have happened if it were closer? The energy flux of the flare at Earth's distance, the amount of energy per square meter per second hitting the top of the atmosphere, was approximately 10 ergs per square centimeter per second. That is enough to ionize the ionosphere, but not enough to penetrate it significantly or affect the lower atmosphere and surface. At 10 light-years, a distance comparable to the nearest star systems beyond Alpha Centauri, the same flare would deliver roughly 25 million times more energy per square meter. That flux would be sufficient to strip the ozone layer on the exposed side of Earth within seconds, exposing the surface to lethal ultraviolet radiation. The ionosphere would be driven to near-complete ionization. The chemical changes in the atmosphere would persist for years, similar to the models of nuclear winter but driven by radiation rather than particulate matter. At 1 light-year, closer than the Oort cloud extends, the flux would be roughly 2.5 billion times what reached Earth in 2004. That level of energy deposition would heat the upper atmosphere enough to cause significant thermal expansion and possibly drive rapid erosion of the atmospheric column. A planet in that radiation environment would have no functioning ionosphere for months. At 10 light-years distance, a Magnetar giant flare of the magnitude produced by SGR 1806-20 is a potential mass extinction event. At 1 light-year, it may be a planet-sterilizing event. The question is, how many Magnetars exist within 10 light-years of Earth? The answer, as far as current surveys indicate, is 0. The nearest known Magnetar to Earth is significantly farther, but the galaxy contains an estimated 30 million neutron stars, and Magnetars represent perhaps 10% of that population. Most have not been identified. Their positions are not mapped. 3 days before the Magnetar flare on December 26, 2004, a magnitude 9.1 earthquake struck off the coast of northern Sumatra, triggering the Indian Ocean tsunami that killed approximately 230,000 people, one of the deadliest natural disasters in recorded history. The international attention and satellite observation capacity that would normally have been immediately directed at the Magnetar flare was partially redirected to the disaster response. This timing is coincidental. There is no known mechanism by which a Magnetar flare 50,000 light-years away could trigger seismic activity on Earth. The energy that reached Earth was real, but deposited almost entirely in the ionosphere, not transmitted to the solid planet beneath. The two events share a date on the calendar and nothing else. What the proximity of the dates created, however, was a data analysis challenge. The satellites that detected the Magnetar flare, RESI, Integral, Swift, the WIND spacecraft, the Messenger probe on its way to Mercury, and others, had instruments that were saturated by the main burst. Several had their detectors effectively blinded for seconds to minutes. The data quality of the main pulse itself is poor precisely because the event was so much brighter than anything those instruments were designed to handle. The tail, at lower intensity, is better characterized. The main burst energy estimates are reconstructed from detector saturation times and count rates in peripheral detectors, rather than direct measurement. It is, in a specific sense, the problem of being too close. A detector designed for the brightest known gamma-ray sources was overwhelmed by something brighter. The event exceeded the instrument's dynamic range. Future instruments have been designed with this event in mind. Wider dynamic ranges, faster readout electronics, detector configurations that allow some fraction of the incoming flux to be measured even during extreme saturation. The 2004 flare was both a scientific landmark and an engineering lesson. The Magnetar threat is not in the same category as asteroid impacts or nearby supernovae. It is less predictable, less detectable in advance, and in the worst-case scenarios, more immediate in its effects. An asteroid impact gives us time if we detect it early enough. A supernova in our galactic neighborhood would be visible as a brightening star weeks before the radiation front arrived. A Magnetar flare travels at the speed of light and provides no warning whatsoever. By the time detectors see it, it has already happened. For any future settlement beyond Earth, the Magnetar question becomes a site selection constraint. The galaxy is not uniformly safe. Regions with higher concentrations of massive stars, where neutron stars and magnetars preferentially form, represent elevated long-term radiation risk. The galactic center, with its dense stellar population, is not just logistically difficult to reach, it is a genuinely more dangerous radiation environment. The galactic disk at our distance from the center, in a region with relatively low massive star density, is safer. That is not a coincidence. It may be part of the reason life was able to develop here. The concept of the galactic habitable zone, the region of the galaxy where the combination of stellar density, metallicity, and radiation environment makes planetary life most plausible, places Earth near its inner boundary. Move inward toward the galactic center, and radiation events like the 2004 Magnetar flare become more frequent and more intense. Move outward toward the galactic rim, and the heavy element abundance needed to build rocky planets becomes insufficient. The band in between, where we are, is the zone where the risks are manageable and the chemistry is available. For colonists in that band, the 2004 event establishes a baseline. A Magnetar at 50,000 light-years causes measurable ionospheric disruption and nothing worse. The atmosphere absorbed the hit. A planet with an Earth-like atmosphere and magnetic field has substantial natural shielding against extragalactic gamma-ray events at that distance. The threat level rises steeply as distance decreases, but the known Magnetar population within the critical radius appears to be zero, and the detection surveys that would identify nearby Magnetars are ongoing. What cannot be planned for is the undetected population. Most Magnetars are quiet most of the time. They only reveal themselves during flares, and many flares are not detected, either because no instrument was pointing in the right direction or because the flare was below detection threshold at current sensitivity levels. The 2004 event was detected because it was extraordinarily bright. The catalog of confirmed Magnetars, currently around 30 objects, represents only a fraction of the total population. Knowing where they are requires either waiting for them to flare or detecting their persistent but faint X-ray emission between events. Both methods have selection biases. The nearby Magnetar population is not fully characterized. The mechanism that produces giant flares is not fully understood. The starquake model, crust fracture triggering magnetic field reconnection, is the leading hypothesis, but the specific geometry of the crust failure and how it couples to the magnetic field to produce a coherent burst rather than a series of smaller events is not modeled from first principles. The 2004 event was the third giant flare ever recorded from a Magnetar, following events from SGR 0526-66 in 1979 and SGR 1900+14 in 1998. 3 events are not enough to build a reliable statistical model of giant flare rates. How often SGR 1806-20 specifically will produce another giant flare is unknown. It has produced hundreds of smaller bursts since 2004, which suggests continued magnetic activity. Whether those smaller events are releasing the stress that might otherwise build to another giant flare, or whether the system is recharging toward a future event of similar or greater magnitude, is not determinable from current data. The question of whether any Magnetar has ever triggered a mass extinction on Earth has been seriously proposed. The Ordovician-Silurian extinction approximately 443 million years ago, which eliminated roughly 85% of species, has been linked in some models to a gamma-ray burst or magnetar flare from within the galaxy. The evidence is indirect. There is no smoking gun geological signature that definitively points to a radiation event rather than the climate changes and volcanism that are the mainstream explanations. But the timing and the pattern of extinction, which preferentially affected organisms with shallow water, high-latitude habitats consistent with ozone depletion on specific parts of the globe, remains consistent with a radiation event from one side of the sky. Finally, the relationship between fast radio bursts and magnetars has been a major area of research since 2020, when a magnetar in our own galaxy, SGR 1935+2154, produced a burst of radio emission simultaneously with an X-ray flare, providing the first direct evidence that at least some fast radio bursts originate from magnetars. Fast radio bursts are millisecond duration radio pulses detected from extragalactic distances, and their energy requirements make magnetars the most plausible source class. If confirmed universally, this would mean that every fast radio burst astronomers detect from distant galaxies is a magnetar firing, and that the 2004 event, had there been a radio-sensitive instrument watching at the right moment, might have appeared as a fast radio burst to a civilization in a distant galaxy looking at the Milky Way. On December 27, 2004, a dead star across the galaxy reached out and touched Earth's atmosphere. The star had been dead for tens of thousands of years. The light of its original explosion reached Earth long before any human civilization existed. What arrived in 2004 was not a new event. It was the echo of stored energy, finally released, finally crossing the distance. The atmosphere held. Earth's magnetic field and the layered blanket of gas above the surface absorbed the hit and converted it into a brief disruption of radio communications and a measurable change in ionosphere chemistry that lasted minutes. Then the atmosphere recombined. The disruption ended. Most of the 6.4 billion people alive on that day never knew it happened. That is the case at 50,000 light-years. The atmosphere is sufficient. The distance is sufficient. The event, extraordinary by every measure of astrophysical energy, was survivable because of where Earth sits in the galaxy and what surrounds it. The magnetar is still there, still spinning at 7.56 times per second, still accumulating stress in its crust, still building energy in a magnetic field a quadrillion times stronger than Earth's. We are at a safe distance. For now, that is enough.